Okay, welcome everyone to our Chemistry Quarter 1 review. We are going to be covering all of the different materials that we've gone over the past several weeks, everything that will be on your Quarter 1 exam that is upcoming. So let's go ahead and get started. You will all have access to this review along with this video and a worksheet for it. So in case you miss anything or you want to study further after this viewing, you are more than welcome to. So before we get into the actual material, we have some study tips for you. Number 1, and this is the most important, please do not wait until the night before the exam to study. Give yourself a few days to review the material and process everything. Number 2, know the vocab. It's in purple on these slides. All of the slides that we have compiled have vocabulary words highlighted in purple just so you know exactly what to look for. And then definitions are half the battle. So if you are able to understand vocabulary and what it means, that is going to help you a ton in the test. Number 3, study together. Working with a partner or a group of friends will benefit everyone. Now, just because some of you may be online or some of you at home versus in school doesn't mean you can't study together. Create a group text or like a group chat somehow. That way you can share study materials, you can have discussions about the material, and that will help you greatly because you might be an expert in one area and one of your friends may be an expert in another. And by working together, you can teach each other tips and tricks to remember the material. Also, ask questions. If you have any questions regarding this test / the study material, please email or talk to your teacher. They're more than willing to help you. And trust me, we would rather you come to us with questions than act like you are good to go when in reality you're not 100% sure on the test material. And then finally, review the slide decks if you need more in-depth information. So this slideshow will go over pretty much the essential information, but if you need further development, as always, your slide decks are always on your Google Classroom and you can reference those at any time. And use the additional resources provided at the end of these slides. Best of luck to you. You guys have got this. You know more than you think, I promise. So, topics being covered. Each of these slides you guys have access to. They are all linked to each topic themselves. And this first part of the video, we are only going to cover Unit 1. So we will be covering from states of matter through pure substances and mixtures. The second part of the video will be over Unit 2. And Unit 2 is everything from atomic theory and the periodic table through quantum. So let's get started with Unit 1. All right, states of matter. This is the very first thing we covered in chemistry. Remember, matter is anything with mass that takes up space. Matter can be defined into 3 sub-states, right? There are 3 states of matter. We have solids, liquids, and gases. Solids have definite volume and shape. Their particles are arranged in a crystalline structure, which just basically means that there is a pattern to the way the particles are arranged. They are closely compacted and there's not much space in between them. For liquids, they have definite volume but indefinite shape. They take the shape of whatever container they are holding. So if you were to pour water into a bowl and then take that water and pour it into a glass, both fixtures would have the same amount of water each time, so the volume stays consistent, but the shape changes depending on what container they're in. Also, keep in mind the particles flow past each other. So the particles kind of slip and slide past each other and they move fluidly. Then finally, we have gases. They have indefinite volume and shape. They take up the amount of space provided to them. They fill the space in which they're contained and particles bounce off the walls of their container. These particles have the most space between them and they also have the most energy. So they are flying all over the place, bouncing off the walls and each other, and they have the most energy. All right, here are the particle arrangements. So there's the solid state, liquid state, and gaseous state. You can see for solid state, you can see our crystalline structure where there's a pattern to how all the particles are aligned. There's a liquid state right here where you can see the particles kind of overlap and slide past each other. And then we have the gaseous state where there's a lot of space in between our particles and they can kind of shoot all over the place, fill the entire volume of the container, and just bounce off the walls. So really quick, before our next slide, you can pause this video and look over these definitions really fast, because the next slide, we are going to have a quiz, or not a quiz, but a question over this. Okay, so which phase of matter has definite shape and definite volume? If you said solid, you are correct. Remember, solids have definite shape and definite volume. All right. Which phase of matter has an indefinite shape and indefinite volume? If you said gas state, then you are correct. It has indefinite shape and volume. It fills the space in which it is contained. All right, moving forward, we have phase changes here. So anytime you are dealing with a phase change, that just means that you are changing in between the different phases of matter. So from solid to liquid to gas, or vice versa. These are the types of changes that occur when you transition from one state to another. So firstly, I want to go over this graph in front of you. You have time and temperature both increasing and passing. So firstly, we start as a solid. Then as we move from a solid to a liquid, that is B with the right arrow sign. So B moving right. We have solid going to liquid. That will be your melting stage. That is a solid changing to a liquid. So think of ice. If you had a cube of ice and you left it out on the counter, ice would melt to form liquid water. Then here at D, going left to right, you have vaporization, which is liquid changing to vapor. You can either say vaporization or evaporation, either one works. And essentially, this is the process of liquid water evaporating and becoming water vapor. So think of boiling water on the stove, right? That liquid is eventually going to evaporate and become gas. Then going in reverse, we have gas going to liquid, vapor changing to liquid. That is your condensation. So you can think of a Coke can, right? If you have a Coke can and you leave it out, the gas within the can will eventually condense into a liquid form on the outside of the can. That's how your cans actually, quote unquote, sweat. Same thing happens in like a shower, or anytime you've got that beating of water on the outside of a substance. That is an example of condensation. Now, if we're liquid going to solid, say we have liquid water and we place it in an ice cube tray and put it in the freezer, you are going from liquid to solid. That is your freezing phase change, going from liquid to solid. So solid to liquid is melting, liquid to gas is vaporization, gas back down to liquid is condensation, and then liquid back down to solid is freezing. So those are the four main ones you'll need to know. But additionally, you do have two other types of phase changes that involve a more drastic change. So for example, anytime you're going from a solid to a gas, like you're completely skipping the liquid step, going solid to gas, that is called sublimation. And then if you have gas, that is skipping the liquid step, again, going straight from gas to a solid, that is called deposition. Vapor changing directly to solid without going through the liquid phase. Okay, so take a second to review these, and then we'll ask you a question or two. All right, now we're going to move on to physical and chemical changes. So a physical change means that there is no new substance created, and that's extremely important. So physical changes do not change the identity of a substance, or rather it's just some sort of change that may alter the appearance or look of the material. Changes of state are all physical changes. So most physical changes are reversible. So changes of state are all physical changes. So when we looked at our phase changes, melting, vaporization, condensation, We might be changing from one state to another, but keep in mind, if we use the water example, it's all still water. If we have solid ice and it melts to liquid water, it was water here and now it's water here. If we have liquid water and we boil it on the stove and it evaporates, it's not changing into a totally new material. It's just water that went from a liquid state to a gaseous state. Another example of a physical change is tearing a sheet of paper into pieces. So you have paper and you can tear it up as tiny as you want, but it's still paper. By tearing it in half, it doesn't change into something completely new. It's still paper. It's just a physical change. Now, chemical change is something very different. That's when a new substance is created. Chemical changes transform one or more substances into different substances. So, like burning wood. Anytime you have a chemical change, a completely new material is created. So, if you think of burning wood, there's no way to reverse that. You have gone from wood to a new ash material. The same can be said for like a bike, right? If we have a brand new bike and we ride it around, but we leave it outside, gets caught up in the rain, it'll start to oxidize or rust. And that rust is actually a chemical change occurring. That aluminum bike has now rusted and created a new material. So, evidence of a chemical change, since physical seems to be a little easier to spot, evidence of a chemical change includes a solid is produced. Now, that solid is often called a precipitate or precipitate. Either one works. So if we look here, this is a precipitate, and that's basically whenever a reaction occurs and a solid material is formed, usually out of two liquids or two aqueous solutions. A change in energy, like light or heat, a gas is produced. So if you guys look at this picture right here, we see these balloons being inflated, right? They are placed on top of these Erlenmeyer flasks above a reaction. So as the reaction happens, it inflates the balloon. A gas is being produced. And then, of course, a color change. So like whenever you left your bike outside and it rained, that brand new shiny metal would rust into a dark reddish orange rusty color. That's an example of a color change. So other than changes, we have to look at physical and chemical properties as well. So here are some examples of physical and chemical properties. So when thinking of chemical and physical properties, you have to think of properties that would alter or could possibly alter the chemical composition of the material. So like density, for example, density is defined as physical, right? That has to do with physical properties of the material itself, whereas flammability, which supports combustion, which combustion is explosions, right? That's a chemical change because it could alter the chemical property of the material. Sour taste is physical, reacting with water to form a gas. So we know forming a gas was an example of chemical change. Therefore, we know that it itself is a chemical property. Solubility, dissolving, right? That is a physical change because just because you're dissolving something in water doesn't necessarily mean you can not reverse that change. Melting or boiling point is physical. Neutralizing a base. Now, you may or may not know what this means yet, but essentially you can balance out the pH levels of certain materials, and neutralizing a base is itself a chemical property. And then react with a base to form water is also chemical. All right. Now, diving in a little more to physical properties, these are going to be more important when it comes to your tests than the chemical properties, because you need to know the difference between the two types of physical properties. They are either extensive or intensive. Now, extensive properties depend on the amount of matter present, right? It depends on the amount. It is a measurement that depends on values. These properties vary with the amount of substance present and therefore cannot be used to uniquely identify a substance. So, for example, mass. If I said I had 100 grams of some substance, you wouldn't be able to tell what it is. If I said 100 grams of substance A or substance B, you would not be able to tell them apart specifically based on that mass value. You that amount does not allow you to identify a substance. Also, mass depends on the amount of matter you have. So if I have 1 gram of a substance or 1,000 grams of a substance, mass changes. Those values mean that mass changes. It depends on the amount of matter present. Volume and length are additional extensive properties. Intensive properties, on the other hand, do not depend on the amount of matter present. These properties stay the same regardless of the amount of substance present and therefore are frequently used to uniquely identify a substance. So, where mass, volume, and length depend on the amount of matter present, density, color, hardness do not. If I said that I had something that's blue, it didn't matter if I had 100 grams of that blue material or if I had 1,000 grams of that blue material. It's still blue. It doesn't matter how much of it I have. Same thing with hardness. If I have 2 different metals and one is harder than the other, it doesn't matter the amount I have. They are hard regardless of how much I have. So keep that in mind. It depends on the amount for extensive, and for intensive properties, it does not depend on the amount of matter. All right, this will be our last topic that we cover in this part 1 video, pure substance versus mixture. So on one hand, our matter can be divvied up into solids, liquids, and gases, but that just defines the state of the matter. That doesn't actually look at the composition of the matter itself. So that's what we're going to do right now. So you can either have a pure substance or a mixture. Now, pure substances themselves are uniform with unchanging composition. Every sample has exactly the same characteristic properties and composition. They exist as either elements or compounds. Elements themselves are found on the periodic table, and they cannot be separated into simpler substances by physical or chemical means. An element is an element, and it cannot be broken down into anything less than itself without losing its properties. Sure, if you had an atom of copper, you could break it down into its subatomic particles, but it would no longer be copper. It would be the protons, neutrons, and electrons that comprise that atom. Now, if you took 2 elements and put them together, you would have what's called a compound. Compounds are combinations of 2 or more different elements that are chemically bonded. So, for elements to become compounds, they have to be bonded together through a chemical change. And then for compounds to be broken down into elements, they have to be broken down through a chemical change as well. Chemical change is the key to pure substances. All right, so then pure substance versus mixture. So we just talked about pure substances. On the other hand, a mixture is a combination of 2 or more pure substances in which each pure substance retains its individual chemical properties. So a mixture can be divvied up into 2 subcategories known as homogeneous mixtures and heterogeneous mixtures. So homogeneous mixtures or solutions are uniform in appearance, meaning if I mixed 2 separate materials together and they looked like one material, it would be homogeneous. Think of chocolate milk, right? So if I took milk and I mixed chocolate syrup in it and I mixed it really, really, really well, there's almost a guarantee that you would not be able to tell the difference between the chocolate and milk. That is a homogeneous mixture. Heterogeneous mixtures, on the other hand, are not uniform in appearance. Individual substances remain distinct and are not blended smoothly throughout. So, an example of a heterogeneous mixture could be like chicken noodle soup, right? Chicken noodle soup is a mixture of all kinds of different materials. But at the end of the day, even though it is mixed, you can still pick out the differences. You can pick out the chicken and the noodles and the broth and the vegetables. You can see and pick out the individual differences. Within heterogeneous mixtures, you're not going to need to distinguish these 2 subcategories. However, you do need to know the difference and the definition. Colloids are heterogeneous mixtures that do not separate on their own, and then suspensions are heterogeneous mixtures that can separate on their own. So they settle. If you've ever left like chicken noodle soup out, that's actually a pretty decent example because you can actually see, especially if you cook it with olive oil, you can see a thin layer of oil settle on the surface of the soup, right? So suspension involves a heterogeneous mixture that actually can separate on its own. Now, a physical change is required to combine pure substances into mixtures and to separate mixtures back into pure substances. So when we form a mixture or break apart a mixture, it is through a physical change. So like mixing the chocolate milk, mixing is a physical change. When you add all your ingredients together to make your chicken noodle soup, you are just adding them and combining them together. That is physical change. All right. And last but not least, this is actually a breakdown of matter into separate categories within pure substance and mixture. So go ahead and review this, and we will have a question to follow up at the end. But after that, this will be the conclusion of part 1. Please review part 2 for unit 2 coverage. Thanks, guys. Have a great day.